My name is Kriesh Tivare, and I'm here to offer an innovative solution to an enduring problem around power transmission. In our current world, power lines are the main source of transportation for our energy. In 2011, in just 1 week alone, Hurricane Irene struck and caused about 7.4 million homes to lose power. In 2016, Hurricane Matthew struck and caused over 1 million Floridian residents to go without power. Based on repeated incidents of weather calamities in relation to power loss, power lines have been proven to be extremely vulnerable to damage from wildlife, vegetation, vehicle collisions, and weather incidents. I have worked to create a more fault-tolerant solution as a replacement for power lines. This new form of power transmission uses the scientific principle of electromagnetic induction.
The basic idea is that when an inductor is powered with an alternating current, it will produce a changing magnetic field. In a demonstration of Faraday's law, the changing magnetic field will induce a current into the second inductor, which can be harnessed for power use. When you couple the inductor with the capacitor, it forms an LC circuit, giving the circuit its own natural frequency in which it operates best at. The frequency is called the resonance frequency and can be calculated using the formula FR equals 1/2 pi root LC, in which L is the value of inductance for the coil and C is the value of capacitance for the capacitor paired with the coil. The circuit is specifically tuned to its resonance frequency in order to ensure that power losses are minimized and maximum output power can be achieved. In order to find the best coil for prototyping my model, I spent weeks designing, 3D printing, winding, and experimenting with coils of different shapes, sizes, and gauges.
This circuit has 25 turns of 28 gauge wire paired with a 33 nanofarad capacitor. I used this circuit as the base when creating my prototype. Later, I made changes to the spool in order to save production costs. This spool was to be much thinner and use much less material, but along with the same wire and same capacitor.
Here, you can see my electrical schematic for my final model. It has a 6-circuit layout, with each unit having an inductor coupled with a capacitor. The first circuit will be powered by my frequency generator with 20 volts and its resonance frequency. The last circuit's output will be displayed in my oscilloscope and can be indicated by the red LED placed on the circuit.
This model is a representation of a neighborhood. It includes a step-down transformer substation, my new form of power transmission replacing power lines, and a household. After power reaches the substation from my power grid, the substation will power the first LC circuit with its resonance frequency. After the first circuit is powered, it will produce a changing magnetic field. The second circuit will be induced with the current from the changing magnetic field and will produce a changing magnetic field of its own, inducing the third circuit, and the third circuit will produce its own changing magnetic field, and so forth until it reaches the final circuit, in which power will be sent into households for power use. To display how fault-tolerant this method of transmission is, you can see that even if one of the circuits were to be damaged, you can see that power continues to be transmitted just at a lower efficiency until it can be replaced. Over multiple experiments, I've observed that the efficiency of power transmission greatly decreases if the circuits aren't aligned, or if they move farther away from each other. The effective way to increase power transmission is by adding more circuits in between the source and the output. For future research, I've made a distinct observation. The resonance frequency of the circuits changes as I align them closer or farther away from each other as a result of mutual impedance. In the future, I want to continue working with mutual impedance, finding ways to effectively increase the efficiency of my power transmission and minimize the power loss between my circuits.